Hello and welcome. In this video we will be taking a look at the second chapter of David Albert's book Time and Chance. So in the first chapter, Albert has given us a puzzle. A puzzle that consists of the fact that on the one hand our world seems very asymmetric in time, and on the other hand the laws of nature are in some sense time reversal invariant. So let's recap that very briefly. The world seems asymmetric in time in the sense that many things in the world happen in one direction and not the other in time. So the future looks very different from the past. People grow older, their bodies age, their bodies don't rejuvenate. Eggs break apart, but they don't reconstitute themselves into whole eggs. I can act towards the future, right? I can make plans for tomorrow. I can't make plans for yesterday and do something about yesterday, right? So the world seems to be extremely asymmetric in time. The future and the past, very different things. Now we might expect to see that in the basic laws of nature that we find in physics. And so it's a bit of a surprise when we find out, for instance, that the laws of Newton, of Newtonian mechanics, are time reversal invariant. That means they don't change, they don't vary when we reverse time. In the laws of Newton, if you change t, time, for minus t, if you flip past and future, the laws remain the same. And so, if it fits the laws of Newton that an egg breaks apart, then it would also fit the laws of Newton if all of those little fragments come together and make a whole egg again. There's no violation of the laws of nature involved. And that is to a certain extent, and Albert has explained this to us in some detail, also true for later physical theories like electrodynamics or even quantum mechanics. And so this is a bit of a puzzle. We have this asymmetry in time, but we don't see it reflected in the laws of nature. What we're going to do now in the book is we're going to delve into two physical theories that people have thought have a lot to do with the asymmetry in time. And those will be the two sciences of thermodynamics and statistical mechanics. Now, thermodynamics and statistical mechanics are very closely related. They are about basically the same kinds of phenomena. Thermodynamics was developed mostly to think about steam engines, and it is about things like temperature, pressure, doing work like pushing on things, for instance, generating mechanical energy like that. It's about volume, it's about, those kinds of things. And so is statistical mechanics. It's about the same phenomena, more or less. But thermodynamics and statistical mechanics look at those phenomena in a very different way. Statistical mechanics looks at them by looking at the particles that make up these systems. So if in statistical mechanics I think about a gas, I think about it as consisting of billions times billions times billions of particles, which are all moving around and bumping into each other. And I'm going to try to understand the system by thinking about those particles. Clearly, I can't do that by thinking about all of them individually. There are way too many. But I can try to do sort of the statistics of them. I can sort of try to describe them as a whole, like talking about their average speed, for instance, or the distribution of their speeds, things like that. And so I can try to understand gases and other systems having to do with heat and work and temperature and so on in that way. So that is what statistical physics does. Now, thermodynamics sort of abstracts away, you could say, from these underlying particles and just talks about the measurable things like temperature and volume and pressure itself. And it tries to give us explanations and laws in just those macroscopic terms. So just the terms that we can measure without delving into the microscopic level. So they're macroscopic rather than microscopic. And when thermodynamics was originally developed in the 19th century, one of the reasons to do it that way was that physicists didn't believe in molecules and atoms. I mean, some of them thought that the world probably consisted of molecules and atoms, but this wasn't clear, right? It could also have been the case that matter was a sort of continuous thing, which was not broken up into little particles, for instance. People didn't know that, and it wasn't until basically the early 20th century, that physicists really came to believe that there are these molecules and atoms and so on and so forth. So thermodynamics can do without particles, and in that sense it requires less assumptions, and it might also be in some ways a bit more simple than statistical mechanics, because we don't have to think about all of those particles. So in this chapter 2 we're going to look at thermodynamics, and then in chapter 3 we're going to make the switch to statistical mechanics, which is after all maybe a more accurate description of what's going on, because there are actually these particles, right? But for now, thermodynamics. Now, a very important concept in science in general, but also in thermodynamics, is the concept of energy, right? And one of the things that is crucial to know about energy is that, according to physicists, energy is conserved, right? There's never going to be, in any change or process in the world, there's never going to be more energy or less energy. The total amount of energy in the world stays the same. And it is, of course, possible for objects to gain or lose energy, but that's only possible by transferring energy to some other object. And sometimes the type of energy remains the same in a transferal, and sometimes the type of energy changes. So suppose that you have a fast-moving ball, right? A fast-moving ball has something that we call kinetic energy. It has a certain mass, a certain velocity, and that means that it is a certain energy which is equal to, you don't have to remember this, maybe you already know it, which is equal to 1/2 times the mass times the square of the velocity. So it has this kinetic energy, this movement energy, and let's say it bumps into another ball and the other ball starts moving, right? What happens? The kinetic energy of one ball is transferred to the other ball. Maybe, on the other hand, the ball bumps into a wall and the wall is not impressed, and it just, boom, I mean, that's what happens. So where did the energy go, right? I mean, the wall is not moving. Well, the energy probably turned into heat. So heat is the name of energy that is in a heightened temperature, in the form of a heightened temperature. So the ball's energy, boom, I mean, the ball warms up a bit, the wall warms up a bit, this quickly dissipates, so you don't really feel it maybe, but that's where the energy went, right? It turned into heat. Kinetic energy turned into heat. So what thermodynamics is very much concerned with are these transfers of energy, either where the kind of energy stays the same, so where, say, a hot object and a cold object come together and energy, like in the form of heat, transfers from one of them to the other, or where one type of energy is turned into another. So if I have a gas in a piston, so a piston is where I could push it to make the volume smaller. If I push it to make the volume smaller, then the gas is going to heat up, right? I have to do work, I have to sort of push, I have to put in some mechanical energy, and the gas is going to heat up. So the work turns into heat. Or if I have some hot gas, I could have it push against a piston, and I could maybe use that energy to raise a weight or something, and the gas would be cooling off, and at the same time there would be sort of work done on this, let's say, this weight that goes up, and so heat would be transferred into work. And the change of the energy of a system in thermodynamics is therefore going to be the same as the change of its heat, so the amount of heat energy that it has, and the amount of work done upon it. And this is basically a version of the law of the conservation of energy in specifically thermodynamical terms. The energy of a system, or let's say the change of energy of a system, is the change of its heat plus the change of the work, like the net amount of work done on it. And among multiple systems, this always adds up to zero, right? If I have an isolated system or an isolated bunch of systems, then energy might be transferred from one part to another, but it's never going to be in total more or less than we ever started out with. So that's one way of thinking about these systems in terms of energy, and energy always is conserved, it always remains the same. And so patently, what we have here, like this first law of thermodynamics, which is basically conservation of energy in terms of heat and work, this is patently a time-symmetric law, right? A law that says that something is conserved, that something always stays the same, is patently time-symmetric. It's gonna be the same if you reverse time, because it says that energy always remains the same. And if it remains the same towards the future, then it also remains the same towards the past. So this law is clearly time reversal invariant, right? It has nothing to do with the direction of time. Okay, so why do people think that thermodynamics has something to do maybe with asymmetries in time? Well, that's because thermodynamics is also very interested in the distinction between reversible and irreversible processes. So there are things that you can do in thermodynamics which you can also easily perform in reverse. I already gave an example. If I have a gas, let's say that I have a gas in a piston, so I could push it in order to make the volume smaller, or I could have the gas push the piston in order to make the volume bigger. Now, if I push it carefully, maybe I use a weight that slowly goes down in order to push the piston, the gas is going to heat up. If I then give the gas the opportunity to push back against the piston, it might push it back, the weight goes back up, the gas cools down again, we end up in the same position that we started out from. In practice, that's going to be hard. There's probably going to be some leakages of energy here and there, but in principle, this is possible. I can compress the gas, and then I can have the gas sort of reverse that same movement, return the work back into whatever system I originally took it out from. So that's a reversible process. But there are other processes which do not seem to be reversible. So suppose that I have a gas in a container that is split in the middle by a little wall, and all the gas is on one side. I wanted to say on the left side, but probably on your screen it's the right side. Let's say the left side. All the gas is on the left side. I take away the wall, bam, of course the gas is gonna expand, right? And now it's in the entire box. And if I put back the wall, it's still gonna be in the entire container. It's not gonna go back to the left side, right? I mean, there's basically no way for me to put it back into one side, at least not by bringing back that wall, right? I mean, that as such is not reversible. And it's a question whether I could reverse it in some other way. I mean, I could try to push it back, but if I push it back, then it's going to heat up. So I have to put energy into it, and it's going to heat up, and I'm not going to end up in the same place where I used to be. So this would seem to be a process that, if you think it through, can't easily be reversed, and in fact it can't really be reversed in such a way that we end up in the exact same position again. Here's another example, maybe even more familiar. If you put something that is hot next to something that is cold, you bring them together, there's going to be a transfer of heat from the hot thing to the cold thing, right? The hot thing is going to cool down and the cold thing is going to heat up. How do I reverse that, right? I can pull them apart again, but that's not going to help me get the energy back into the hot system. In fact, there's really nothing I can do that only gets the energy back into the hot system. I mean, I could start heating up the hot system again and cooling down the cold system again until they were back where they were, but then I have to use a lot of energy and stuff to do that. I mean, I've got to build a refrigerator, I've got to turn on the heater. I'm not going to end up in a situation that is identical to the original one. And so it seems to be the case that some things, some processes in nature can happen in one direction without changing anything else in the world, but they can't happen in the other direction without changing anything else in the world. And this is the basic idea of the second law of thermodynamics. So what is the second law of thermodynamics? Well, there's a bunch of ways to think about that, a bunch of ways to formulate it. The German physicist Clausius phrased the law as follows. He said, it is impossible to transfer heat from a colder system to a warmer system while no other changes take place. Right? So you can't transfer heat from a cold thing to a hot thing without changing anything else in the world. And of course, the other way around, it's very simple. Right? You can very easily transfer energy from a hot thing to a cold thing without changing anything else in the world. You just put them next to each other and it's going to happen automatically. But you can't do it the other way around. Right? You can't take a cube of ice and a hot piece of metal and then somehow use the cube of ice to heat up the piece of metal. I mean, that's just not going to happen. So that's how Clausius tells us that the second law of thermodynamics, that is the second law of thermodynamics. You can't do that. Here's a different formulation of the second law of thermodynamics. And it might sound like a totally different law, but it's actually just a different formulation of the same law, arguably. So Lord Kelvin, the British physicist, tells us that it is impossible to take heat from a system of a uniform temperature and use it to do work without changing anything else in the world. Right? So you can't just turn heat into work. That's the basic idea. You can change heat into work if you have a temperature difference between parts of your system. So if you have something that's hot and something that is cold, then you can actually use that temperature difference to do some work, and that is how a steam engine, for instance, works. Right? You have a hot fire, you have some cooler water, you boil it, it puts something into motion, it cools down again, and then you can heat it up. But you need the fire to be hotter than the water for that to work. Right? You need a temperature difference. If a thing just has a uniform temperature, then you can't use that temperature to do some work without, basically getting energy or work for somewhere else in the world. So without changing the rest of the world. One of the things that Albert does in the chapter is he shows with some very simple examples how these two laws of Clausius and Kelvin are actually basically the same. If it were possible to change heat into work without making any other changes, then you could also have a cold object transfer its heat to a hot object. Because you take the cold object, right, you make it do some work, like maybe raise a weight or something, and then you use that weight to heat up the hotter object, maybe by bumping into it or something like that. If you can break Kelvin's law, then you can break Clausius's law. If you can break Clausius's law, then you can break Kelvin's law. So they basically turn out to be the same thing. Two different formulations of this second law of thermodynamics. Now, everybody's favorite formulation of the second law of thermodynamics is this. It is that entropy cannot go down. So we can define something called entropy in thermodynamics. And basically you do it like this. You say, well, the difference in entropy between two states is the difference in heat divided by the temperature at which the system was when the heat was transferred. So the difference in entropy is the difference in heat divided by the temperature at which the system was. And if you apply that to these different thermodynamic systems, you're going to see that if that's your definition of entropy, and you make the claim that entropy can't go down, then you actually sort of get once again the Clausius and the Kelvin formulation out of it. So here's how to get the Clausius formulation. Suppose that you were able to transfer heat from a cold object to a hot object. Then the entropy of the cold object is going to go down. It's going to go down because it loses some heat. And the amount of entropy that it loses is the heat difference divided by its temperature. But this is a low temperature, so if you divide by a small number, it doesn't change as much as when you divide something by a big number, right? It doesn't become as much lower. So this is a relatively high amount of entropy. Let me rethink how I was phrasing this. Okay, you know what? I'm not going to try to do this calculation in front of this camera right now. This works better with a piece of paper that I can show you, and I don't have it right now. If you look it up in the book, you will see that, giving this definition of entropy, you can show that you get the Clausius formulation out of it, or the Kelvin formulation if you want to. If heat was to be transferred from it's actually, okay, no, let's do it. Okay, I'm gonna renege my reneging. I'm going to do it anyway. So suppose that we have two systems, and let's say that one of them has a temperature which I'm going to call 1, and the other has a temperature which I'm going to call 2, right? And 2 is bigger than 1. And now they transfer, let's say, 10 heat from the cold one to the hot one. How much entropy is lost by the cold system? Well, I said the difference in entropy is the difference in heat divided by the temperature. So here the temperature is 1, we lose 10 heat, 10 divided by 1 is 10, so we lose 10 entropy. Okay, the hot system, how much entropy does it gain? Well, it gains 10 heat, but the temperature is 2, and 10 divided by 2 is 5, so it gains 5 entropy. So 10 entropy is lost, 5 entropy is gained. In total, 5 entropy is lost, right? Minus 10 plus 5 is minus 5. Well, that is exactly what can't happen according to the entropy version of the second law of thermodynamics, right? You can't lose entropy. And so, according to this version of the law, it is impossible to transfer energy from the cold to the hot object. The other way around, on the other hand, well, if I transfer 10 heat from the hotter system to the colder system, the hotter system is going to lose 5 entropy, the colder system is going to gain 10 entropy, and so in total the entropy goes up by 5, and that's fine, because the second law of thermodynamics says that entropy can't go down, but it can remain the same or go up. So the entropy version of the second law of thermodynamics allows you, or allows it in the world, that heat goes from hot to cold objects, but not that it goes from cold to hot objects without any changes in the rest of the world. Okay, so here's how we can see that this entropy formulation works in practice. And basically, all these different ways of formulating the second law of thermodynamics are equivalent, right? It doesn't really matter which you use, but the entropy one is usually the most useful one because it has the shape of a formula and you can plug it into for lots of different systems and just calculate with it. So that's the most popular one. Now, at this point, it might seem as if we have done something very, very mysterious, but also maybe very important, because it seems that we have found a law that is asymmetric in time, that is not time reversal invariant, that is, to use a fairly horrible phrase, time reversal non-invariant, and it is the second law of thermodynamics, right? The second law of thermodynamics tells us that entropy can't go down. Well, it means entropy can't go down as we move towards the future, right? So if we look at the world and we look at the total entropy in the world, well, suppose that it always remains exactly the same. I mean, then we wouldn't really have an asymmetry. But if we see that it goes up, then that is allowed by the second law of thermodynamics. And if we flip it around in time, then we would see entropy going down, and that is not allowed by the second law of thermodynamics. And so it certainly looks as if this second law of thermodynamics is not the same if you flip it around in time. Because entropy can't go down, flipped around in time becomes entropy can't go up. And that's a very different law, and one that clearly isn't true. And so what we have done is we have apparently found a law that is time reversal non-invariant, and so maybe a law that might explain how it is possible that the world is so asymmetric in time. And this is in fact how the idea of entropy is often used by a lot of people in a lot of discussions about asymmetries in time. It is used to explain why those asymmetries exist. But this is a very mysterious thing to have done, because supposedly, right, whatever is going on in those thermodynamic systems is governed by the basic laws that describe the basic elements of that system. Right? So we do in fact believe, of course, that all these systems are, they consist of small particles, and all those small particles are governed by sort of the basic laws that are sort of Newtonian laws or electrodynamic laws, or maybe quantum mechanics laws if that becomes important at some point. But they're governed by laws that are symmetric in time, that are time reversal invariant. So how is it possible for a system that is built up out of things that are governed by laws that are symmetric in time to then not be symmetric in time? Where does this asymmetry come from? Nothing we have said so far in thermodynamics explains that. So thermodynamics basically tells us, based on what we see happening, gases expand into a container that's empty, but they don't then suddenly, without you doing anything, go back to a small corner. Hot and cold objects only exchange heat in one direction, from hot to cold, but not in the other direction, from cold to hot. Like, that's the kind of stuff we see. That's a good reason for us to believe the second law of thermodynamics, to formulate it, to believe it, to use it. It seems to be time asymmetric, right? Time reversal non-invariant. And yet we don't have an explanation of how this is possible. And so if we want to understand what is going on, we need to delve deeper. We need to go on to chapter 3 of Albert's book and think about statistical mechanics. Right? Think about those underlying particles. And one of the things we're going to see once we do that is that, strictly speaking, the thermodynamic version of the second law of thermodynamics is not quite correct. It's not quite true. It is, in particular, not quite true that entropy can't go down. Entropy can go down. It's just that sort of large diminishments of entropy are extremely unlikely. And so we're going to have to think about that. We're going to have to think about things like probabilities. We're going to have to think about what are the ways in which the second law of thermodynamics doesn't quite hold. And we've got to think about how that interacts with the ideas of time asymmetry or time reversal invariance if we want to understand what's going on. So that's going to be the burden of chapter 3 and, by the way, later chapters. One more thing that Albert does in chapter 2 is he introduces one little piece of terminology which I think it's useful to repeat here. It's the idea of an equilibrium state. Right? So the idea would be that if you have a system that is sort of stable in terms of its volume, in terms of the environment in which it is, and so on and so forth, then although that system might not be at that moment quite in equilibrium, it might still be sort of internally changing in terms of the things we measure in thermodynamics. So maybe, for instance, I've got a gas in a container, but one half of the gas, like the left side, is hotter than the right side, which is colder. Or maybe at this moment the gas is still in one part of the container or something like that. That would not be an equilibrium state, right? It's still changing. But after a while, a system is going to tend towards this equilibrium state where, let's say, the gas in the container is everywhere equally, has the same temperature and is everywhere equally dense, maybe. Or if it's in a gravitational field, other things might happen, right? We can make things more complicated. In a gravitational field, the gas is going to be a little bit denser at the bottom of the container than at the top, in the same way that in the atmosphere, like in the air around us, like at sea level, the atmosphere is denser than at the top of the Himalaya or even higher up in the atmosphere. So there could be different equilibrium conditions. An equilibrium condition doesn't have to be uniform throughout, but it's stable, right? The equilibrium condition is a stable state. And it also turns out to be the highest entropy state, right? So here we again seem to have a certain kind of time asymmetry. If you leave them alone, systems go towards equilibrium, and that is the same as going towards the highest possible entropy that the system can have. And so again, we seem to have this asymmetry, right? We go towards equilibrium, not away from it. We go towards high entropy, not away from it. Again, it's very mysterious at this point in our book how this is possible, and we want to know more about that by delving into statistical mechanics.